Hello and welcome to today's video. In this video, we're going to talk about differentiation rules. Similarly to the rules for working with limits and continuous functions and functions in general, there are a number of rules for working with derivatives of functions. These rules make it easier to obtain the derivative of a given function from its building blocks. And in this video, we'll start the discussion of these rules with the first few differentiation rules. So this section is called differentiation rules. We'll start right away with the first, probably the practically most important rule that you usually don't think about a lot, and that is the linearity of differentiation. So here's the theorem about the linearity of differentiation. As usual, we want an open interval, so let I subset of R be an open interval, and we want to point x star in I. And let's say we have two functions on I that are both differentiable at the point x star. So if f and g, functions defined on the domain I and with codomain R, are both differentiable at x star in I, then we can combine those two functions. We can take the sum, the difference, or any weighted sum, or in general, any linear combination of those two. So for arbitrary values, lambda and mu in R, the function given by lambda f plus mu g, that's a function again defined on I and with the codomain R. This function is also differentiable at the point x star. And furthermore, the derivative of that function, d by dx, of the function lambda f plus mu g at the point x star, is given by lambda f prime at the point x star plus mu g prime at the point x star. So for a weighted sum or difference, you can just differentiate the functions making up that sum separately and then sum up the results. In other words, what you could say is that differentiation is a linear operation. Now, let's make this notion a little more precise. What do we mean by saying the derivative is linear or the differential is linear? That's a remark here. Of course, if you want to talk about linear mappings, we'll first have to define a suitable vector space. And the vector space is called C1. C1 of I, more precisely, and that is the set of all functions with domain I and codomain R, such that f is continuously differentiable on I. And continuously differentiable means the derivative f prime is a continuous function. Now this is a vector space, and we can define a mapping on that vector space. Let's have a look at the mapping that assigns to each function, to each element of that vector space C1, the derivative of that function. Then this mapping is called the differential operator. And it's often written as D, capital D. That's a function from C1 to C0. You will remember C0 is a set of all continuous functions. So differentiating a continuously differentiable function, of course, yields a continuous function. So the result of that differentiation will be in C0. So this differential operator, defined as d of f, is the function f prime. And this differential operator is a linear mapping. And of course, I already mentioned that C1 is a vector space. So that is the precise version of saying differentiation is a linear operation. That means the differential operator as a mapping is a linear mapping. Okay, now that has been the first, probably most important, but also the easiest differentiation rule. You probably do this right without even thinking about it. The next two differentiation rules are a little more complicated, and you have to know about that and apply them correctly. So here's the second theorem of this section here. And those rules are referred to as the product rule and the quotient rule. They're not as straightforward, and proving them requires playing around with the definition of the derivative a little. I will not go into the details here, but I'll let you know about the rules. And of course, we'll practice how to apply them. So as usual, we have an open interval. So let I subset of R be an open interval. Let X star be a point in I. And let F, G be functions defined on I, codomain R, that are differentiable at X star. Then the two rules are, first, the product of f and g. The function f times g is again differentiable. So that's the product rule. The function f times g, again a function defined on I, of course, is differentiable at x star with, and here's the product rule, f times g prime at x star. So the derivative of this product is equal to the following expression. You first take the derivative of f, so the first function, at x prime, at x star. You multiply that by g, the function, not the derivative. And then you add f evaluated at x star times the derivative of g at x star. So there's two summands, one derivative in each of those, and one non-differentiated function. So this is product rule. And the second rule of differentiation is the quotient rule. So for expressions of from f divided by g, we'll apply that one. And of course, g has to be equal to a number that is not 0 at the point in question. So if g of x star is not 0, then the function f divided by g is differentiable again at x star, and the derivative can be computed as follows. The derivative of f divided by g at x star is given by the following expression. That's a little more complicated. You first take the derivative of f at x star, multiply that by the function value of g, then you subtract, you don't add, but you subtract f at x star times g prime, and all of that is then divided by g at the point x star squared. So this is the rule for taking derivatives of quotients of two functions. So whenever you have a rational function, for example, you'll make use of this quotient rule. Let's have a look at two examples to conclude that section, to get a little practice. First example, we've already talked about affine linear functions, and we've talked about monomials, so functions of the form x maps to x to the power of n. Of course, we can also apply the rules that we've just had and consider polynomials now. And of course, every polynomial is then a differentiable function because it is composed of monomials. It's a sum of monomials. And according to the linearity that we've had in the first theorem, then a polynomial will also be differentiable. So every polynomial p of x, and let's say the polynomial is of the form sum from 0 to n, some coefficients ai times x to the power of I. Every such polynomial is differentiable on R as a sum of monomials which are differentiable. And we have also talked about the derivative of a monomial. So we can also get the derivative of p, so p prime at x. What you have to do is just keep the constant as it is, and the derivative of x to the power of I is I times x to the power of I minus 1, with the exception, of course, of x to the power of 0, right? So x to the power of 0 is 1, the derivative of 1 is just 0, so that part vanishes, and all the others are differentiated accordingly. So what we get here is I times ai times x to the power of I minus 1. And we start the sum at 1 now instead of at 0, because that term for I equals 0, the constant term of the polynomial, that vanishes. And you notice that is, again, a polynomial. The degree is lower by 1, at least by 1, but it's still a polynomial. Yeah? So on a more abstract point of view, we have defined a mapping from the space of polynomials to the space of polynomials through differentiation here. Part B, let's also have a look at the quotient rule. And let's say for some n in n, we want to consider the function f of x defined as 1 over x to the power of n. So we take the monomial x to the power of n and we invert that 1 over x to the power of n, which is the same as x to the power of minus n. Then how about that? Well, of course, this is not differentiable at the point x equals 0 because it's not defined there. But for all others, we can apply quotient rule. So for x not equal to 0, we obtain f prime of x is equal to, well, what do we have to do? We first take the derivative of the numerator, that is 1, so the derivative is 0, multiplied by the denominator. Then we subtract the derivative of the denominator times the numerator. The numerator stays, so this is 1 times, and the derivative of x to the power of n is n times x to the power of n minus 1. And now this is divided by the denominator squared. So x to the power of n squared. We can simplify this a little. This 0 times something vanishes. So we're only left with this part here. And that means what we get here is, let's take out the minus n. We take that to the front here. And then we have x to the power of n minus 1 divided by, well, x to the power of n squared is the same thing as x to the power of 2n. And this quotient here, that's the same as x to the power of n minus 1 minus 2n. So what we get here is minus n times x to the power of minus n minus 1. And what you can see is, again, this is formally the same rule as you'd apply for monomials of a kind x to the power of n. You take the exponent here, you write it in front of the expression, so the minus n comes to the front, and you reduce the power by 1. So instead of to the power of minus n, it's now to the power of minus n minus 1. Right? So that rule also applies to negative powers. And we found that out by applying quotient rule. So that concludes this introduction into differentiation rules. Of course, there's more than these rules, but we'll go into more detail about those in one of the next videos. And I'm sure I'll see you then.